Hi everyone, and okay, does this work? Amazing. Little bit of introduction. I do security announcement for the web at Google, and I've been using Go for roughly 4 years now. My main interest was brought me into programming when I started fiddling with a new computer, and my first computer didn't have multi-core. But the second one did, and I wanted to use it. But at the time, I was writing languages that didn't really empower me to do so. I started writing some parallel code. At a certain point, I discovered a monster, which is contention. So contention, by definition, is a competition, is a race between two or multiple things to try and acquire the same research. Doesn't mean if it is for reading it, writing it. If you're trying to do the same thing at the same time, you're going to contend to try and get it. And since I'm an engineer, I try to face a problem in a very scientific way. So first thing, let's measure it. If you have multiple cores working on the same data, you're going to lose efficiency. You're going to waste computational power because you're trying to, basically every core is going to smash on the feet of the other one, trying to do the same thing. Go, one of the most amazing things about Go is that it comes with tools. It's one of the few languages that allows you to do almost everything with just one command. And of course, we also get the pprof tool. When you run your code, you have two ways, basically, to collect a pprof. One is to run tests, or from the code, just import pprof, open a file, output a pprof there, or you can also capture the profiles live. This is very important because I don't know about you, but production usually breaks. Production usually gets slow. You run stuff in QA and it's perfect. Test environment runs like a charm. You push it to production and then it just becomes slow. And it's important that you can collect traces and pprof live by just importing a package. I wouldn't advise to continuously collect those, but you can, like, every hour collect a minute of traces. And that's good enough because it allows you to see stuff. Let's see one example. This is a code. I declare a variable, let's call it A, somewhere, and then I spawn many Go routines, and each one of those is going to increment that variable many times. But since I don't want a data race, I need to protect that variable with a mutex, which is mu. So basically, the entire code of this program is lock, increment, and unlock from many, many different Go routines. And they're going to do that many times. The pprof tool has the web command, which I use a lot because I'm a very visual person. And that is the first box that shows up. It tells me that the flat time spent in my function, which is content func1, because it's a closure, it's 0.04 seconds. The cumulative time spent in this function is 2.4 seconds. So where am I wasting my time? If you expand this a little bit, the output of pprof is a lot more. It's that entire SVG. And first two blocks, most of my time was spent trying to acquire a lock. I don't know about you, but I don't think this is useful work that I was doing, because I was just basically doing nothing. I was waiting. This is not good. And you can also see it not just by the CPU profile, which is what you're looking at behind me, but you can also run your toolchain with a mutex profile. That is Supersize because it allows you to see the exact line of where you spent maybe too much time acquiring a lock, like in this case. And this is useful because when you're trying to debug a big code base, not like this is just 11 lines. When you're trying to debug a big code base, and in production you see you're going slow, but you don't see why, these highlights where you spent, like, you can do top 10, and it gives you the top 10 functions in which you wasted time waiting for a mutex. This is a lot of features, and I would advise anyone to just try it out. Open it up. exploded help is very well documented, unlike trace. So trace is the other tool. I've tried to make sense of all the things that are in here. I didn't manage, but some of the things actually provide insightful and intuitive data. You can collect traces with test trace or as pprof to just import it. One of the links that you find in the main page brings you to this view. This view, if you have trace regions enabled, allows you to see some interesting data. So one is, first part, it tells me that I had 4 coroutines in that region. That region was entered 4 times. And 3 of those took 10 milliseconds. One was slightly shorter. If you have many, many coroutines that enter a region, this allows you to see the tail latency. If you're interested about latency, if you're interested about performance, tail latency is what you're really looking for, because the slowest one is what your users are going to complain about. So this view is crucial, and it also gives you a breakdown. If you click on those links, for example, on the 3 coroutines that entered the region, you get a nice table with a breakdown on everything you did. So this takes 11 milliseconds, and execution time was 7, and I spent like 0.2 waiting, and the scheduler spent 4 milliseconds out of 11 just trying to find out where I should run my Go routine and when. This is, of course, not good. If you don't have regions set up in your code, you can always click on the Go routines link. This doesn't give you much more information. Actually, it gives you less, but still, is good enough. If you don't want to spend too much time instrumenting your code base, this is on by default. You can get this with 0 line changes. And it's the same table as before, so not bad. There is another tool, which is obscure, undocumented, made by engineers for themselves, which is the trace view. This doesn't give you much information about the lock time spent, but it allows you to see how many cores you're using at the same time. So if you're spending too much time contending the same resource, at a certain point you will see in the above view that not all cores are used. So you will see some coroutines hopping here and there and cores waiting. That is bad, but this view is not very insightful for contention. Now I'm going to give you one information. I like to measure, which you should like to measure, but there is one problem if you try to measure too much, is that your tools and the things you measure influence the measure. So while I was working on this talk and I was doing some research, I found out at a certain point that I was measuring the trace code. I wasn't measuring my code. I was measuring the time spent in garbage collection to release, acquire memory for the trace. So don't measure too much, maybe. Before we go on, I would like to warn you. Contention is bad, but it's rare. So sometimes it's going to burn up a lot of power, but that means that when it burns too much power, you should address it, but it's not always the case, so don't change without measuring. So this is 3 Go routines that write and 3 Go routines that read. Might be a channel, but it might be something else in between. This is how it looks to you when you write code. This is how it looks for the hardware. So this is just bottlenecks. You're trying to do too many things on the same shared state. And mutex and channels are just structs blocked by a mutex. And that is not good. So there are some ways to address this problem. And that means that you should look at the data. You should know how your data is, how your data looks, and how your data behaves. One common way is stop sharing everything. You probably don't need that shared state. If you know the ratio of the producer versus consumer pattern, or the setters and the getters, you can just break them up, and when you spawn them, you connect just a few of them with each other. That just relieves those channels, because now you have 2. You just divided the contention by 2. Another way is just try to contend less. So instead of every time you have an update, tell the channel, update, 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 you just batch it up and just contend less. You just collect everything together, and once every while, you just push all the changes to the state. Now, don't try to be better than the standard library at implementing a mutex. I've seen people switching away from mutexes and trying to use atomics instead. It makes no sense because that's what a mutex is. If you don't contend your mutexes, you're just going to change an atomic to a value and change it back afterwards. You can't get faster than that on modern hardware, so don't. This is the end of the safe zone. So if everything goes good, you just have to care about that kind of a contention, locks. But sometimes you realize you're writing code for hardware, not virtual machines that run on rainbows. So look at this code behind me. I'm spawning as many coroutines as core, and then I'm creating a slice that is that big. So I have 4 cores, I spawn 4 coroutines. Each one of those is going to write an integer of that slice. So one time is going to be a slice of 4 bytes, and one time is going to be a slice of int32 and 164. And I just run them, and they write a lot. So the 64-bit version of these will write 8 times more bits than the 8-bit one. So which one would you say is faster? Who says the one that writes more? Who says the one that writes less? The middle one? Wow. OK, so since no one is guessing, yes, the faster one is the one that writes more. When you see these results, you're like, good, I understood nothing. I've been coding for 15 years. I have no idea what I'm looking at. Because you need to go into the hardware. When you write stuff, you don't write it directly to memory. You write it to caches. And caches have to synchronize. And that means that every time you change something in a slice that is too small, so it ends up being the same cache line, you need to synchronize with all the other cores to say, hey, I changed this. Can you please pull it? That means that every time you change something, it goes back to L3 or main memory and then comes back again. So writing a full cache line is faster, even if you have to write more. That means that when you need to, for example, acquire a read lock, a read mutex, you actually need to write to memory. So if you think that just reading from a data structure that is locked by a read mutex is just going to read, you're wrong. You're writing a cache line to say, hey, there is one more reader. That means that you're invalidating the cache of all the other cores. This sometimes is insignificant, and this sometimes can bring you to implement a new data structure. There is one in the standard library you can use, SyncMap, if this happens to be the problem. But I would suggest to just use this in case of emergencies. Like, you should see the glass in front of it with break in case of fire. Because this map is not simple. Just to give you an example, the methods of this data structure receive pointers to a struct with an atomic value that points to a struct, with a map that points to a map header that points to a hash table whose elements are themselves pointers to atomic pointers, to interface values that point to concrete values that might themselves be pointers. Don't use this unless it's necessary, but this is much faster because it avoids the problem that I talked about before. If a map is not what you need, you might want to go raw and use atomics directly. I tried. You have to think a lot. If you do this, the race detector will not work. So you're alone in a land of fire, and it causes some headaches. I have some code in this slide that allows you to have a very simple example on how you can read and write a value atomically, releasing a lot of pressure without using a mutex, which is just to read, you just atomic load it. And to write it, what you do is you load, you change it, and you bet. If this hasn't changed since I loaded it, swap it. Otherwise, I reload and retry. This is more cache-friendly, creates some problems, so do it at your own risk. And that was it. How much time do you have left? Oh, I thought, oh, my clock is wrong. Okay, so I can go back to this slide. So, as I said, those conditions are very rare. It's almost impossible to end up in a case in which you need to use this stuff, but I've seen this in production, and I've seen this taking down some services. I don't know if you've heard of some outages that have been recently happening in some of our services, but one of the reasons is that we're trying to contend the same state across different servers. And if this affects multiple services, it's not just cache that you're invalidating. You need to go to the network every time you fail something. You need to synchronize. So you should probably look into this at that point, measure it, make your changes, and be sure that what you're changing improves performance. Because I've seen this code, this exact code, making a program slower. The reason for that is that you should never guess. Never guess about performance, and never try to improvise. Just go to your tools, go to what they output to you. pprof shows you much more than what I showed you. It also shows you, for example, when you compile your code, you can see many, many more information. You can also tell the tools to tag your code and say, for example, at this line, I couldn't do this because that data structure is too big. You can get warnings on what is the struct going to appear. So if we go back to this example, we have 4 Go routines that write to the same slice. If I wanted to reduce the contention, because what I need to write is a byte and not a full 64-bit int, it doesn't really make sense to write a 64-bit int and do the byte operations manually. You can just pad. So instead of creating a slice that is 4 big, you just add some bytes that you don't use in that slice, and you just change the one that you need. This allows you to release the contention on caches, and you just change the data that you actually want to change without too much hassle for the hardware to keep up. You can do the same with structs. So when you declare your structs, if you see you're going to change, for example, 2 different Boolean values or 2 different bytes that are one next to each other, declared in the same struct, and you know you're going to change that across different threads that run concurrently and in parallel, you might want to add some padding. In Go, the syntax is very simple. Let's see if I can pull up an editor. So can anyone see these? So if you have something like these, these might become very contended. If you know that your cache lines are going to be a certain size, and you should know that because you should know where your code run for service, you can just do this. This tells Go, hey, there are 2 variables here. I call them underscore, so I cannot name them again anymore. I can't set those without using unsafe, and if you use unsafe, you should feel bad. And when I compare my structure, when I do everything with this, it's like those variables don't exist. But this tells the compiler space. Give it space. Do not put them together because I know what I'm going to do. Most of the stuff that I talked about is about knowing your data, knowing what you're going to do. If you end up in this situation, it's very hard to measure and pick up, but it's also pretty easy to solve. One more thing, mutexes. How many people here have used a mutex? Good. If you have a central state, it's very easy to put a mutex on it, and that's it. You're race safe. And if you're race safe, that's good. But if you just start contending it, you should know how to split it. Because it's very tempting when you have like a dictionary to just break it down by letter. I mean, the alphabet is breakable, so you just split in different buckets, and you say, hey, A is going to be a bucket, B is going to be a bucket, and that's very good. But let's say that the things you're putting in buckets are Java packages. How big do you think is the bucket for com going to be? You're going to hit that very same mutex every time, so you're not improving. You're not doing anything. This is called the zip flaw. That's one of the reasons why the state of caching in general programming languages is very, very bad. Because in order to write a generic code that knows what is going on and releases contention and works very well, needs to know what is going to end up in there, which is something I usually don't know. So if you're using a cache, you have a custom-built cache, or you have some data that you need to access across different threads, you should probably not just measure contention, that's it, but also look at your data. One of the most common things for me when I do this stuff is to print it out. You just throw a terminal at you with a lot of data scrolling in. You try to aggregate it, query it, and you should find where is the right point to break, to split, especially with your production data, because this is stuff that you cannot find if you just use QA environments. And this is why the pprof tool that allows you to pull profiles in production is very important. Final word. I have a link for these slides, and in these slides there are several links, and I guess, I know we are not doing questions, but since my clock was wrong, we can have 5 minutes for questions, if that's okay. So, questions, anyone? Yeah? Okay, so I wrote double underscore just because I was supposing a 32-bit cache line, but I mean, it could be 8, 9, or 12. Or every underscore that you put as another shadow variable that you cannot set or read. So it depends on the hardware that is going and is running. Also, don't trust benchmarks too much, because I've seen benchmarks completely change even on the same architecture. So if you're like running on x86 or running on ARM, you should probably rerun your benchmarks. But even if the hardware is supposed to be the same, it's not, that doesn't necessarily mean that it is the same and might work differently.
Who else has a question?
Well, I can repeat the question.
Thank you for your talk. I listened to some talks about Kotlin, and there they say for channels, they improve the channels, and they refer to Go like channel having a single like mutex to add and to get the data out of that, and then they invent some really complicated mechanism to use channels without locks. And
so yeah, channels in Go had a proposal to go lock-free. And that just added a lot of complexity. And if you go lock-free, usually you're not just giving up locks. If that was easy, everyone would do it. You're giving up also other things. For example, order and some guarantees that channels nowadays give you. Going lock-free for channels, so implementing a fully multi-producer, multi-consumer, lock-free queue, is not something you can easily do. And when you do that, usually you sacrifice other things, which is either code reliability, guarantees, cross-platform performance, and functionality. It was discussed and discarded.
Okay, we're going to let everyone go for lunch. If you have other questions, tweet.
Yeah.
Lunch is in the same place that breakfast is served for the hotel, I guess. It's out and to the left. An hour and a half.